All right, so NLP transformers for information extraction from large documents. I'll probably ask Tina to give a brief introduction about our group and in US Bank, and then I will walk through some of the stuff that we thought would be interesting for this group. Tina, do you want to kick it off?
Yes, sir. So hi, everybody. Thank you so much for having us here today. We are super excited. So Sumitri and I come from the same enterprise AI group at US Bank. So what we do is we look at all of the use cases and business problems across the entire bank, and then try to figure out where can we automate process, where can we reduce risk and detect fraud and be more central to our customers' lives using AI and machine learning or advanced analytics techniques. So Sumitri leads the entire enterprise AI R&D innovations, as well as all of the complex techniques that he's going to be walking through with you today. One of them is NLP transformers here. So with that, I get to work with him in terms of how do we use his awesome innovations and models and codes and techniques and apply that into a business system and really get results to solve real life issues for our customers. So that's who we are. And I'm going to send the ball back to Sumitri to begin the presentation.
Great, thank you, Tina, and thank you, Justin, for this opportunity. I thought we're talking about NLP transformers, and this is applied AI. I thought we should probably start with an interesting article. This is an essay on social distancing. And it's a very interesting essay. I'll just read through some of the highlights of this. It starts off with, I'm sure you have all seen those carefully worded and rather difficult to understand notices that warn people living in places where there is a contagious disease that they must avoid meeting each other on the street. So that's how it starts. It's got a little bit of a negative connotation about social distancing. It does talk about contagious diseases. We've been very familiar with social distancing. Social distancing is a word that I actually didn't know until COVID hit. And then this essay starts talking about how, friends have to behave in front of each other as strangers because they can't really shake hands or give hugs and things like that. And I found that to be a very interesting essay. You may or may not like the tone of this essay. It may actually be that, hey, social distancing is required for a contagious disease, and why is this essay with so much negative connotation, and there may be others who find it amusing. And if you have not guessed, this essay was not written by anybody. It was written by a transformer-based NLP model. So it was written by GPT-3, and this essay was generated in summer 2020. What is the more interesting thing about this essay is not the fact that, okay, GPT-3 has come up with an essay on social distancing. The more interesting thing about it is that this model had stopped training in October of 2019, before there was any COVID even discovered. And the model was trained on all kinds of scientific data, Wikipedia kind of data, book corpuses, and things like that. And it is able to come up with a very interesting essay on a topic like social distancing, which before COVID was completely non-existent. At least to me, I didn't even realize that this was a scientific word. Uh, so that's the power of these language models. Um, and this model, GPT-3, was built with a transformer. And we'll talk a little bit into how we got in to this point where a transformer-based model is now able to craft really nice um, essays all by itself. This was unheard of even about 2-3 years ago, and the fact that this is happening now with this level of accuracy is really appalling. Um, so a little bit of about myself, and I'm not going to go too much into all these details. Um, I am now a leader, AI leader at US Bank, and one of the main things that we see is that we are a very regulated industry, the banking industry, and there are a lot of checks and balances. So what I'm going to be talking about today is extraction of information from a very large document or large documents. But this needs to be motivated with why do we need to extract information from these large documents. So I'll try to go through the following outline. I was just talking to Justin before the talk started. I had not made any kind of assumptions on the technical level of the audience. And so for some people, this may be a little bit lower level. I do think that I get a little bit geeky towards the end, and we'll see if we have time, we can go into much more details and much more geeky stuff. But I just want to first give you a motivation for a typical NLP problem in banking and finance and why we need to do something like this. Then we'll talk a little bit about how did we get here to the transformer architecture. What were we doing before transformers? And then, so that is a journey that will take up most of my talk. And then towards the end, we'll give you a motivation for how we solve the problem that I'm going to show first. And then maybe towards the end, we can talk a little bit about where things are going. And this is where the multimodal stuff and other things that I talked about just before the presentation started can take us. So the problem that we are trying to solve, one of the problems is we have a lot of different problems in the banking industry, in general, US Bank in particular, but the problem that we are trying to solve is a problem that's called LIBOR transition, right? And for a lot of people who may not know what LIBOR is, I pulled this slide out from a World Bank presentation. LIBOR is basically a base rate. It's a rate that is coming from the London Interbank offered rate. And if you ever took a adjustable rate mortgage, your adjustable rate would have been based on the LIBOR rate. And so the LIBOR rate is basically a good proxy for how the lending rate is between banks. And that's how it was set up. But in 2008, it went through some very serious scandals of fixing the rate by different banks and things like that. And so the US has decided that we will shift away from LIBOR. Unfortunately, mortgages, if you think about them, are 30-year mortgages or even sometimes more than that. Commercial loans are even more than that. And if somebody comes in and says, by 2021, we have to get rid of LIBOR and base all of our mortgages, contracts, and everything else on a different base rate, that's the kind of problem that we are facing right now in the banking industry. You can think it is a miniature version of the Y2K problem, because you have these contracts that have been written up. Um, Sometimes they span 1,000 pages and even more, and you now have to sift through these contracts, which are could be 30 years old or 25 years old, and then pull them out and then essentially issue a new contract. So World Bank also said, hey, look at all your financial products, look at all your contracts, look at all your systems, and then make the changes so that all LIBOR linked legal contracts can change. And they also say assess the strength of a fallback language. And what fallback language essentially means is that when somebody signs a contract and it's based on the LIBOR rate, that contract may or may not have the provision for what rate would the contract use if LIBOR becomes unavailable. And so that is called fallback. And so some contracts have very nice fallback language. They say, hey, if LIBOR becomes unavailable, then the contract will continue based on this other rate. And some contracts don't have that. And so what we needed to do was, first of all, sift through all the contracts and mortgages and CDOs and things like that that are based on LIBOR. Uh, Pull them out, read through them, comprehend them, and then pull out the paragraphs that have this fallback language and then assess whether that fallback is strong enough that we don't need to restructure this loan or this contract, or do we need to actually now restructure the loan. This is a generic problem that everybody in the banking industry is facing. And if this has to be done before 2021, then it's really a daunting task. So I know this is an open forum, and we're talking about some of the contracts that we deal with in US Bank. I don't, there are some contracts that are out in the open, and I thought maybe we can just take a look at some of the contracts that are out in the open. And just to see, this is a contract between Noodles and Company and US Bank. It's out in the open, so I can talk about it. And if you can see it, this is a pretty daunting document. It's got around 300 pages, and there are certain places where it really talks about this rate that I was talking just now. So here it says, hey, look, if this is based on LIBOR, if a comparable successor rate is there, then you can, and it is approved by the administrative agent, which is US Bank, then you can use that rate. So this is a fairly okay fallback, but it doesn't tell you what the successor rate is. And so these are the kinds of problems that we have to solve. And we are trying to solve these problems with AI. So what we want AI to do essentially is
I'm just
is to read through the contract. And if there are any amendments to the contract, read through the amendments, extract certain entities like borrower or a lender, payment terms, base rates, how much above the base rate is the actual rate, that's called the spread margin, things like this. And then also find these paragraphs that I just showed you. And find also paragraphs that talk about implication of change. If you change this contract, what happens? Is there some kind of indemnity that either gets nulled or gets activated? These are all things that need to be taken care of when you are recreating a contract. And this is a hugely daunting task if you don't have a automated means of reading through the document and identifying certain things. And this needed to be done before December 2021. Now, because of COVID, it's been changed to 2023. But still, it's a very daunting task. And so, how do you make a computer do this, right? How do you make a artificial intelligence system that can actually comprehend these contracts, look at those contracts, and try to read it and try to extract information from it? Simple keyword extraction will not work, right? Because multiple people are writing these documents and multiple people uh, use different languages to write these different type of language and style to create these contracts. Um, so what we really need is maybe to try to build a language model, and that's what we set out to do. And at about the same time, 2018 is when a very nice technique called a transformer came into existence, and we are uh, at the moment trying to use the transformer technique uh, to see if we can solve this problem. So for the next few minutes, I will try to walk us through how we got to this point where we needed a language model, and how we got to the point of using transformer for solving the kind of problems that I just referred to. Reading through a large swath of documents, figuring out what's in them, and then figuring out what needs to be changed. Uh, so that's the problem that we had to face. And the way we started off with is we need to try to teach this computer how to read these documents, and for that the way to do it is to build a language model. So I will not go too much into detail about how you build a language model or anything like that. But what in general is a language model is essentially, if you're given a partial sentence, can you come up with the next word in the sentence? And that in itself is a language model. If you can do that, then you can do multiple things. You can first start building the next word in the sentence, and the next word in the sentence, and the next word in the sentence. And you can build a paragraph, and you can build an essay like you saw in the GPT-3 example. You can do other things. You can basically mask out one of the words in the sentence and say, can you predict what is this? Can you fill in the blank? Um, and if you build a good language model, you can also solve that task. And then finally, if you really have a good language model, you can also solve problems like the SAT or the ACT tests. You can give a paragraph and ask a question about the paragraph, and try to get some answers. If you have language models that are multiple languages that we use, then you should be able to use AI to translate from one language, for example, English, to another language, German or French or Hindi or something like that. So these are all things that you can do if you have a good language model. So what is the simplest way to create a language model? The simplest way to create a language model is to create a network that learns, given a few words or a few letters, what is the next letter. And in this case, you're trying to just uh, say, okay, HELL, and what is the next letter? And obviously, the next letter, if you ask anybody here, will say it's O, right? Because it's you're trying to say hello. But how do you make a computer learn this? We use things called recurrent neural networks. And so what you do is you basically take each of these and represent them as a number, and then you train this network in essence by giving it a lot of language examples. And then the model will start saying, oh, you started with hello, uh, and or you started with HELL, and then it comes up with hello, and then it comes up with the space next, and then it starts a new word, and it can go can keep going like that. Question is, can you do that with just letters? So this is a very nice example of what happens if you train this network, right? There is no fancy tensor flow. There is nothing here. There's just two equations. And this simple network, if you start training with the whole works of Shakespeare, this network will start creating Shakespeare um, like outputs. So it has at some point learned that, okay, there are certain words that come, and so this network has never been taught that produced is a word, upon is a word, but the reverse of upon, written in the reverse direction, is not a word or anything like that. But the network has learned that. Um, so this is with Shakespeare. You can do the same thing with other languages. I did it with Sanskrit, which is my and written in my mother tongue. And first time you start doing it, it comes up with gibberish. But you keep giving more and more input data, it will learn by some time. It will start creating poetry. Now, this poetry may not mean anything, but at least it has learned the structure of the language. So this is how people started these language modeling. And so for us, how we start using these language modelings is to use these recurrent neural networks by varying the different inputs and the outputs. If you provide a set or a sequence and you ask for one output to come out of that sequence, this is called sentence classification or paragraph classification, and Twitter sentiment classification. These are all examples of that. So this is one thing that we use quite a bit in our applications. The other one is what is called a token classification or named entity recognition. That's another way to say it. And that is to take a set of tokens or set of words and generate another set of words or numbers or anything like that. So in this case, if you give English, you can generate French, and if you give a large English paragraph, you can generate a zero for all the words, a one, for example, for all the words that are people's names, and a zero for everything else. And if you do that, that's essentially named entity recognition. So it's called token classification. So that's what you try to do with recurrent neural networks. And then once you have something set up like this, you can also start looking at it. Instead of looking at this sequence like this, you can also start looking at it in the reverse direction. And why is looking at a sequence in a reverse direction more interesting? For things like this. If I state something like the movie is terribly exciting, until I read the word exciting, this gives you a very negative connotation. As soon as I insert the word exciting, it changes the complete meaning of the sentence. It's a very highly positive connotation. So for things like that, it is good to read from the left, and it's also good to read from the right. And you have the luxury of doing that when you're dealing with large documents and you're trying to deal with recurrent neural networks. If you're doing speech recognition or something like that, you don't have this luxury, because you're reading or you're taking a sequence and you're trying to basically create a sequence on the fly, and that is a little bit more challenging, because you can't read from left to right and from right to left of the whole sentence. But you can do that if you're dealing with these kinds of paragraphs and things that I talked about. And so these are called bidirectional RNNs or bi-RNNs. Again, I'm not going to go into too much detail about how they're set up and all the equations. There used to be another way to do these bidirectional reading. You can read it through the words. You can also read through just the letters. And if you remember the Shakespeare example, that was done with just letters. So why not combine them, right? So you can combine reading letters in this bidirectional RNN and reading words also in this bidirectional RNN and come up with a combination. And there used to be a package, or there is still this package that, but it used to be hugely popular, and it was called Spacey. And before Transformers, this was almost the king of the world. Everybody used these um, this architecture to come up with extraction. So if you look at this sentence, Mark Watney visited Mars, what you need to do is to say, okay, Mark Watney is the name of a person, so that's what you're trying to come out with. And then Mars is a location, and that's what you're trying to come out with. So this is a simple token classification. For our case in US Bank, if there is a paragraph here, which is not a paragraph like Mark Watney visited Mars, but a big paragraph from a contract, we need to be able to pick out, okay, this is the LIBOR rate, and this is the borrower, and this is the uh, lender, and things like that. So that's where the analogy comes. And a lot of us NLP practitioners used to use this um, architecture for doing these extraction. And then came along another way of doing it, and that is to derive the word model from the character model. So here in this case, you do the same thing, but you derive the model for George, and you derive the model for Washington and things like that, and say, yeah, George and Washington are a person. And that is because I've read through this way and through this way, and I know that was born will refer to this Washington as not a location, but the name of a person. So these are the techniques that people started using. And once you start using these techniques, you can do something more interesting. And that is to say, why should I just do this on the contracts that I need to look at? Why can't I start doing this on a huge bunch of contracts that I can get offline? And this is called pre-training. So instead of just concentrating only on your set of documents, you can basically say, let's all pool resources and let's everybody get together and create a pre-trained model. And that pre-trained model is trained not just on the contracts that you want to look at, but it is pre-trained on Wikipedia, it's pre-trained on book corpuses, it is pre-trained on a huge swath of information. And if you pre-train it on that, then you can basically use that information from that pre-trained model and combine it with the model that you are trying to create, and then use the combination to come up with a better way of detecting, okay, New and York together are a location that we're talking about. New is not in a separate word than York. So these are all things that you can learn by slowly building this language model. So this example here that I'm showing is from something called TAG-LM, and which was a precursor to another language model called Elmo. And what Elmo did was very similar. It just took the pre-trained model, but it said, hey, I have a better way to pre-train this model. And that is that I am going to try to create a language model which will uh, predict what is the next word. And when I'm predicting what is the next word, the internals of this are the ones that I'm going to store so that I can get a good representation of the word happy. So this model again came and said, let's pre-train, let's use the large swath of information that we have. Wikipedia is one, book corpuses is one, Common Crawl is another one. So these are all good corpuses that you have for NLP, and that's what people started using. Fortunately for NLP, this kind of information started proliferating in the internet as soon as the internet started exploding in people's lives. For vision, it did not have that kind of luxury. There were actually people who created millions of images and annotated those millions of images. With NLP, you didn't have that. So now you have ways of creating good representations of a word. Then you can start combining these words into sentences. And this is a good slide that shows, okay, if I now take these sentences together and I have a representation, a vector representation of these sentences, which can come through representation of the words, how does this context come about? And it turns out that because you are training this on these large swaths of information, when you start looking at these sentences, you will find that these sentences are very nicely clustered in their meaning. So in this case, if you take the passive and the active voice, you will see that they tend to cluster together. Um, and So these types of relationships and things like that are now being able to be captured in a sentence. And if you can capture it in a sentence, then you can basically create a network that captures information and then throw it around to another network that says, okay, I'm going to capture that information that you just gave me, and I'm going to build up a new thing. And those types of networks are called sequence to sequence networks. And those are the ones that are most useful for us to picking out things, because you can think of this as, okay, I have this sentence, it is giving me a meaning for this sentence. I can throw it to another network, the whole meaning. And then that other network can start picking up this sentence and start translating this into French, or summarizing it, or expanding on it. So these are all things that you can do with sequence to sequence. And that's essentially what this gave us. But when you go to sequence, there are two things that you can do. One is that, hey, I'm going to take my um, network that is capturing the context or capturing the meaning of my sentence, and then throwing it to another network to convert it to another sequence. Or I can also somehow make sure that I can give this context in conjunction with what you are trying to predict. So for example, if you are trying to take an English sentence here as the source, and you're trying to come up with a French sentence as a target, as soon as you finish the first word that you predict for your French sentence, you can go back to this network and say, can you give me the context vector in this sequence, so that now you know that I am trying to find the next sentence to this one. So, and a good example of that is abstractive text summarization. So let's say that you have this source text, and this source text is, Germany emerged victorious in a 2-0 win against Argentina on Saturday. This is all a big paragraph written by somebody. And you're trying to come up with a abstractive text summary of this. You can always just take this whole paragraph and give one context. But then the other way to look at it is to say, hey, I just came up with the start and Germany. What is the best next word? And once you tell this network that I already came up with start in Germany, then this network can actually predict the next word much better than it it can if you didn't give that information. So that is called attention. Without going into any kind of mathematical details, this is essentially what made transformers possible. And what happened was that during the early years, people started looking at this attention networks and said, hey, instead of throwing the whole context, you should probably ask for the context every time you came up with a partial sentence. And so you send a query to this network, and this network will take that query and then come up with an attention score or a context vector that you can then use to basically come up with the next word that needs to be put here. And that attention will be different because what are all the things that are coming up? What would be a good summary that comes after Germany? It's the word beat. And to come up with this word beat, the things that are most relevant are the word victorious and the word win. And so if you can compute that, now that I have come up with the start in Germany, the next word that needs to be put in this sequence will have to pay attention to the word victory and or victorious and the word win. Then you will come up with the answer, which is beat, which is basically Germany beat Argentina. That's essentially the summary that you're trying to come up with. So that's how attention was used for the very first time. And then once you have this, you can actually start creating interesting maps. And those are what are called attention maps. And this is a good example of an attention map. So you take a sentence like this: Russian defense minister called Ivanov called Sunday for the creation of a joint front for combating global terrorism. So this is a big sentence. You're trying to find a good summary of this. And so at each point, when the network is trying to create this summary, what are the 2 or 3 words that it paid the most attention for? So after Russia, what are the 2 words that it paid attention for? That is, you can get that information from what is called an attention map. And this is how those attention maps look. Um, there's a lot of math behind creating these attention maps, but you don't have to worry about that. You can look at it to understand this concept. You can look at it as an attention map that is sequentially built as you're creating this sequence out of this sequence. So when people looked at this, a couple of researchers in Google basically came up with another idea, which they said, you know what? Instead of throwing this context vector and trying to come up with the context vector based on this network here, this attention is the one that is more important than anything else. And so you actually don't need much other than the attention. And so if you can compute the attention and you do it at different layers, you will be able to understand this language much more better than this network that was trying to capture one context vector for the whole sentence was trying to do. And that's how transformers came into being. And this is a more profound concept than just what I was just referring to, because all you're trying to do is to say, let me look at a sentence and try to understand in this sentence, when I am building some kind of translation to this sentence, what are all the words that I need to pay attention to? And those are the only things that actually matter. It also turns out that if you're just doing attention, and attention maps, the way the map that is used to create these attention maps is based on dot products. And those dot products essentially mean for computers that you can run them parallelly, or you can run them in a graphical processing unit. Before that, people used to run these sequences, RNNs, in graphical processing units, but it would be sequential, one after the other. Uh, what this gives you is, if you think that only attention and getting the attention of these words um, will give us a good indication of the language, then you can actually build the language on a larger set of data much more quickly, because you can run it in a parallel way. So that's the main reason that this became very popular. So when we say, okay, it runs in significantly less time to train, another way to look at it is that if you want to train it on all of Wikipedia and all of Google Books and all of Common Crawl, it will take a week, whereas the previous one would have taken months. And so that's the advantage of this type of architecture. So this is how the transformer was born. And transformer essentially says, all I need to do is to take this sequence and uh, try to pay attention and try to come up with the attention scores of something on the decoder side. So here is the math, and we'll not discuss the math at all, because the math is essentially the math to generate the map that I showed you before, which is this map. But one other innovation that these guys did uh, is something called multi-head attention. And what does multi-head attention do? Instead of saying each word here is a long sequence of numbers, they said, for each word here, I want to understand if this word is a noun, if this word is talking about emotion, if this word is talking about some other aspect of language. And if I want to do that, then I need to try and find a smaller subspace, which is a projection of this big word. So this is a big representation of the word Germany. You can basically, now that you are dealing in vectors, you can start projecting this to another subspace. And in that subspace, the meaning of the word Germany will be, this may be the noun subspace, this may be the possessive noun subspace, and whatever be the case. So you have these projections into different parts of or different interpretations of a language. And now when you're doing attention between two words, you're now not just doing attention in the big space, but you're doing it in the subspace, in a smaller subspace. So the computation itself, instead of doing a dot product between two numbers that are 512 dimensional, you're doing it in a smaller subspace, which is only 64 dimensional. But you can do this all in parallel, so that will also speed up your computation. So that's what they came up with. And without going into too much detail about any of the math behind this, all transformers do is that they get to a smaller subspace that has some language meaning. And once you get to a smaller subspace that has some language meaning, you will be able to understand the context, and you will be able to pay more attention to the more relevant words. So here are some of the examples of that. So this is an interesting example, because if you look at this example, it says the animal didn't cross the street because it was too tired. The only thing that changes the context between it and uh, and the animal, right? So here it is referring to the animal. If I said the animal didn't cross the street because it was too wide instead of tired, then it is going to be referring to the street. So how do you make a language model understand which word that this which word it should refer to. The way to do that is to basically go down to smaller subspaces and try to come up with some kind of relationships in smaller subspaces. So that's what is being shown here. You can actually, once you start building these models, you can do some very nice visualization of where each of the word is attending to in what subspace. And so in this case, these are 8 subspaces. In this case, there are 2 subspaces here. And in each of these subspaces, there are different types of attentions happening. You can actually go to those subspaces, or refer to those subspaces and try to understand what is happening there. And so the one other thing that they did is that instead of just doing it in one network, they basically said, now, well, because I can run this more parallelly, I can do this in multiple layers. And so each one of these can be replicated 6 times, 12 times, 24 times, and so on. And so this one change is the only change that happens between different transformer models. BERT is one transformer model, RoBERTa is another transformer model, GPT-3 is another transformer model. So if you use n is 12, because so you have 12 layers stacked up, that's how BERT does it. And GPT goes to 96, I think, or GPT-3. So, but the architecture is essentially this, nothing else that changes. So that's what we saw with the transformers. And but if you're doing that, then instead of one map, you get multiple maps. This map that we saw for just one sentence to one sentence will now get sliced into 12 layers and 12 heads. So you have a matrix of matrices. And that's why you have to deal with tensors when you're doing these large networks. But each of these pieces is, if you remember, is a projection to a subspace that is learning something new about the language. And so you can actually start sending probes and say, what is each of these things learning? So that is something that they started to look at in another kind of network called BERT. But before they did that, they said, okay, sequence to sequence is great. Can we build a language model, just a language model from this architecture? The language model you can build from an architecture, but if you remember the language model, when we first started off, we said, given a set of words, what is the next word? That is the language model. But if you want to build a language model with this architecture that is paying attention between words and different words in a sentence, how will you be able to do that? And the concept that the BERT guys came up with is what is called self-attention, which is to take a sentence or a paragraph and start attending different words in that sentence and that paragraph to each other. In doing that, you will first learn the meaning of that paragraph, because you will learn how each word is connected to the other word in the network. And if you learn that, then you can basically say, I am going to mask out some of the words. I'm going to basically blank out some of the words. And I'm going to try to teach this network to learn those subspaces in such a way that the masked out word is picked up by this network. And that's what made BERT and transformer based architecture for word for BERT very popular, because they started doing self-attention. So again, there's a bunch of math here. I'll not go through the math. But what BERT did was something very similar to what we were talking about before, which is to take a sentence like, so it takes a sentence like this, right? The man went to a mask store and then he bought a gallon mask. So you should be able to fill out that this is a grocery and this is off and things like that. So based on that, they built up a model, which is very similar to the model that I was talking about before, which is a model that has learned the generic language based on everything that is used to train it. And that language, essentially what Google tried to do was to use a huge set of uh, information to build this language, Wikipedia and book corpuses and all that. Now, after you're done with the training. Now you have this model that has actually learned the different meanings of the words, and it has learned uh, how different words are related to each other. And once you have that, then you can take this model and then add a few other small things to this model, and this is called fine tuning. And you can start doing things like named entity recognition, or you give a question and a paragraph, and you say, okay, can you find the answer to this question in this paragraph? And this network will be able to learn, will be able to give you the answer to that, because it has learned through this pre-training how this question relates to this paragraph, what's in this paragraph that you can answer based on this question, and it will come up with the answer from the paragraph. So that's one example. Other examples are named entity recognition, which is basically you give a paragraph and say, what are all the borrower names here? And what are all the LIBOR terms here? And what are all the terms that you're looking for in this network? And the network will be able to pick those out. So for that, you do need to do what is called fine tuning. Um,
Hey, Sumitri?
yeah.
There's a question. It says, what are the typical compute resources used to train a transformer? I know there's a lot of different transformers out there, but I mean, I'm assuming there's a lot of data here that needs to be crunched. I don't know if there is any sort of general
Yeah, I
typical
can.
amount, but just thought I'd ask.
Yeah, so I can tell you about BERT. So I was just going to go to the uh, um,
Just the training.
fine tuning model, right? But before the fine tuning, if you remember, I said there should be a pre-trained model, right? This is where you take Wikipedia and book corpuses and all that. So this takes about 8 to 16 GPUs, uh, and um, and will train for about a week.
A week, okay.
And so normally people, I mean, we in US Bank, for example, have not trained models here. What we do is fine tuning, and fine tuning basically taking a model that is pre-trained by Google or by Facebook or OpenAI or somebody like that. We take that and then we do fine tuning on it. And for fine tuning the model, we take about 2 to 3 hours. This is a
Okay.
huge difference on a single GPU. Whereas on the other one, you're using 16 graphical processing units, and it takes a week.
Sure. It sounds like a big energy savings as well, too, just from a
Correct,
pure,
because you're not trying to learn everything from scratch. You just learned
right.
so you take a generic model that either Google or Facebook or OpenAI based on that architecture gives you, and then you train it on your models or your documents, and then you will get what we call as, in this case is LIBOR BERT.
Sure. Good for the environment, I guess, right?
Yeah, it is good for the
Understanding.
environment. So, but then one other thing is, the most important thing is, as I was saying, these are projections to subspaces, and they are the model is learning something new within itself in those subspaces. Is there any way you can use those subspace learnings uh, um, in your task? And the answer is yes, actually. So you can, instead of taking and retraining on your documents, you can just take the learnings, basically whatever, no retrain, right? You just take exactly the same model that Google or Facebook or OpenAI gave you, And then you say, I am now going to take the output of this model. And now, based on the output of this model, I'm still going to create a smaller network on top, but I am going to use all the learnings that BERT has about language. And I'm going to take those learnings and try to embed those learnings in my smaller network. So in this case, also, you're saving energy and you're saving time, because even this type of doing stuff works very well, because you're making use of the learnings that came out of BERT within it. So one way to do it is to just take the top, but there are other ways to do it, and we'll very quickly go into those kinds of other things. What this is basically something that is out of the BERT paper, and the first way, which is in this pentagon here, is to retrain it, right? So you retrain BERT, take the base model and retrain it for your task. And then the second one is called a feature-based approach, where you are only using the features of the BERT and not really doing any kind of training here. Now you take the features out and you say, I'm going to take those features and try to build a network on top. When Google published this paper, they basically had both of these techniques for named entity recognition, and this is the task that we have basically in US Bank. This is one of the big tasks that we do. So the question really is, and they said you can do both, but for the most part, this is what people use a lot today. This actually is, from a practical sense, is very advantageous. And so what we have found is a combination of these two is the one that solves your problem for the most part. And so when we say, okay, what is it that you pick from this network? And remember, this network is a tensor of different types of attention maps and things like that. Do you pick it, if you go back to this picture of this matrix of matrices, do you pick this part, just the top layer or the top matrices, or do you pick some of these matrices? Do you actually take averages of these? There are different questions that you can, there are different ways you can do it. And what the BERT paper tells you is, hey, you can just take the second to last layer, you can take the last hidden layer, you can take a weighted sum of all the layers, or just the top 4 layers, and each of them has some kind of an advantage, and they show this. And so I think it behooves us to say, if the literature, or if the BERT paper and the transformer paper is showing some advantages of looking at inside the network itself, maybe you can probe this and see what is happening inside the network, and maybe we can use it. And so that's what is essentially some of the techniques that we have developed, is to make a combination of these two things and start using them. So before going too much into detail about how we use them, here are some of the examples of what happens in each of these networks. You can actually go into the network and look at what is each of the words in your sentence looking at or attending to. So SEP in this case is just a separator. And so there is one sentence here, and then after that there is a separator, and then there is another sentence that is flowing by. In some of these matrices, and so if I say 1, 1, I refer to the first head and the first layer. In that matrix that I was referring to, is the first one, the top and bottom left one. And then here is 3 and 1, and this projection has learned that there is a lot of importance in trying to see what is my next word. And so it has learned that I don't need to pay attention to anything else but my next word. And you'll see this kind of attention span. And then here, this projection has basically learned that I need to make sure that I can separate sentences. And so it is basically attending to different sentence ends or separators. And another one has basically learned that it should attend to the period. So these are interesting stuff, but there are other interesting stuff that comes out. So there are certain things. It is the transformer is actually trying to learn the language and the grammar. And so some of the things that happen is that direct objects will start attending to their verbs in one of these heads. So this is a projection of some grammatical piece of a language that the network is learning. None of these are things that we have explicitly stated for the transformer to learn. These are things that the transformer has started learning, and when we probe and we go in and see what is this thing doing in each of these subspaces, that's when you will start looking and discovering these interesting stuff. So in one of the heads or in one of the subspaces, you'll see that, plug in funds and then discuss plans, it's a line. So those are in one case. And then in another case, you have these noun modifiers, which is like the complicated language. What kind of language is it? And then what kind of law is it? The huge new law and things like this. These are modifiers for a noun. And with 94% accuracy, if you go to this head, you will be able to determine this relationship. Any noun in that, if there is a modifier to that noun, like the executive, and then there is a modifier called, the 45-year-old executive or the former executive, you will get that. So this is interesting stuff. And we have not explicitly trained the network on any of this. More things, possessive pronouns, passive auxiliary verbs. These are all things that are being learned by this architecture. So just by the fact that it is looking at these different words and then it is trying to see find a projection of each of these words into a smaller subspace and then seeing how two words interact in that smaller subspace, it starts looking, or it starts finding things. And these are only found after you train it and you start probing it. And you say, okay, what is this head actually doing? And if you're not really interested in what it has found, you would not really find any of these relationships. But that's the interesting part of the transformer architecture. And that is that the architecture that is able to understand and comprehend language and grammar and try and is able to find nuances of grammar that we were taught explicitly when we were kids. It's able to actually grasp that in its architecture. So that, to me, that's the most profound thing when I read this paper on how to probe these transformer networks and what is it that these networks are learning, right? So the possessive, Maguire's autograph, his autograph, things like that are the ones where there is the maximum attention, and you will see that in each of these subspaces. So if and then there are multiple other things that you can get from that. So what does all this mean? So what it all means for us is that we can now go back and look at this architecture here, where we take a combination of this and a combination of this and say, we should use both these techniques. We should first try and change and retune the network to our task, and that is basically called fine tuning. We should also go and try to learn the nuances, or try to take the nuances that the network has learned and use those nuances to try to pick out our task. So
Hey,
this,
Sumitri, can I ask you a quick question, like
yeah,
very quick? So the question is that I read the paper too. I had a little difficulty understanding is, you know how you showed the multi-heads, one head pays attention to the possessive nouns, the
yeah,
other one is pronouns, the other one is noun modifiers, whatever, right? Uh,
yeah.
are they, I don't think they are related, but you correct me. Do these patterns form on their own, or do the heads communicate with each other to say, hey, you know what, I'm going to take care of this part of the language. I, on the other hand, am going to take this part of the language. I didn't get that in the paper, but please correct me.
No, they don't. So
Yeah.
that is the interesting part, is that there is more stuff I can talk about when, but they do not do that communication. In fact, actually, you will see that if you start looking at, if you see this one, the first head and the third head, they attend to things that are more broader. And once you go to top more layers, you will see 8 and 9 and 7. These are the places you will see these co-reference and things, and 5 are the ones where you see these co-reference and things like that. So they
Okay.
do not
Thank you.
communicate. They do not communicate with each other. They have basically learned it, and the interesting thing is that they have learned it in this fashion. When you say I have 12 heads and 12 layers, which is what BERT did. If you try to do the exact same thing on another transformer network where you don't have that many heads, or you don't have that many layers, you will probably get a different head um, layer number for,
Different breaks,
yeah,
different breakups. Yep.
different
Yep.
places. But
Yep.
in general, they do, they are learning these aspects, right? It is basically a compatibility network that the network is learning, right? If this is like a match.com, it is basically going down to the communication subspace, or think of it that way, right? In a communication age subspace and other kinds of subspaces, and basically creating a compatibility matrix
Yep.
between different words. Anyway, so coming to how we used it. So what we did was we basically used both these uh, uh, techniques, right? So we take this, we transfer this as is, but we build a LSTM or RNN on top. And we also use this, and we use ensembles of both of them. And it turns out that if you use these ensembles, and you do ensembles of using these two, along with Elmo and with Flair, with the character embeddings. The one interesting thing that I didn't mention yet is that this is all based on words. But in the very beginning, when we were looking at things like the Shakespeare stuff, that's based on characters. So you can actually combine things that are coming out of this, and you can do what is called a stacked embedding, where you take the embedding that is coming out of BERT, you take an embedding that is coming out of Elmo, and you take an embedding that is coming out of Flare or any other network, and be able to do that uh, um, stacked embedding. And we do that, and then the combination of these two networks are the ones that we are able to use to sift through these really large documents and say, yeah, I can pick out the borrower name, I can pick out the payment frequency, and things like that. So without going into too much detail about the actual contract, these are some of the results that we have. On the left hand side is the test accuracy, or basically accuracy on about 200 documents or 200 contracts that we ran these models on. And for somebody who's a data scientist, the word accuracy here is actually not correct. Let me first explain what we mean by accuracy here. But for somebody who's a practitioner of the LIBOR remediation, this is actually the accuracy. So in this case, what we mean by accuracy is, are you able to pick up in a loan document, if the origination date is what is required, are you able to pick up the origination date in the loan document? Are you able to pick up the borrower name in the loan document? Those are all the things that this accuracy basically refers to. So it basically says that in some cases we are very good in picking up, and in some cases we are, we are like at 70 and 67%. But this is still very good given the fact that you look at this document and it's this long. Not only that, we also can hone in on a paragraph that has something related to it. So if we are not able to pick the exact thing, we can at least provide the person who's going to be doing the review the paragraph that you are most likely to find this. And in that sense, with the paragraph, we go up to more than 95% accuracy. But that is accuracy, and I don't want to go too much into detail about what these accuracies mean for LIBOR or anything like that. I think the graph on the right is a much more interesting graph, in my opinion. And that is, the graph on the right is the teal is the individual accuracy of the fine-tuning model. And the gray is individual accuracies of the model that uses the internals of the transformer model and basically gets the features and uses the features to extract the information. Interesting things that you can see, and I don't know if you can read this, but this is a borrower address, and none of the models are able to pick the borrower address very nicely. But if you look at our borrower address, we're at 91%. And how is it possible? And the answer is that the transfer learning models or the fine-tuning models are trying to hone in on certain aspects of an address and picking that address, whereas the models that are trying to learn or that are trying to look into the internals of the BERT model and picking things up from the internals of the BERT model, they are able to pick other aspects. And the combination is giving us very high accuracy, even though any single model is not giving us that much high accuracy. So that's the interesting thing about using the internal features of a transformer, using the internal features of a language model like Elmo, using the internal features of a character-based language model like Flare or Spacey or other things, and combining them is going to help you quite a bit in reading really large documents and getting in information extracted out of these documents. So a few where are we going stuff, right? I think a couple of people asked about multimodal stuff. So this transformer architecture is not really something that you can just do with words. People have started saying, started now experimenting with, what if I take a picture and I cut it into smaller pieces, and then I use it as if it's a sentence. So here it is an interesting example of a picture. It says licensee of McDonald's. And so this picture came from a receipt, and this paper called Transformer OCR is a paper that just got published 2 days ago. 2 days ago was this paper was published. It's called Troker or Transformer OCR. And OCR is very important for us. And so, of course, as soon as it got published, all of our attention went to this paper. And OCR is important because, all of our contracts and documents are stored in files, and they are like, 15, 20 years old. And we need to be able to read those documents from scanned images. These are not PDF images where you can search. They are just uh, contracts that were signed and they put through a Xerox machine. So you get a picture. And so you now have to be able to read the picture. So for something like that, Microsoft just released this model called the Transformer OCR. It's still out. None of us in US Bank, I don't think anybody has actually had the ability to test out how effective this is. If you read the paper, they have some really good claims. And I am looking forward to testing this out. But what they did is very interesting. They just took the transformer architecture, just like I was showing you before. And instead of saying, hey, I need a sentence and I need sentences to start matching with each other, they took something like a picture and they cut that picture into smaller pieces, and then they flattened it out to be like a sentence of these. So you take the top parts and you take the top parts, and then you take the bottom parts and you make a sentence, and then you put the sentence through this architecture. And once you put this sentence to this architecture, you get some results out, and then you pass it through a decoder, and the decoder is able to come up with the actual uh, output of what's in the picture. And so it's able to read what's in the picture. So this is, you think of this as English and this is French, but instead of actually passing English words, now you're passing pictures of English words. So this is a very exciting new way of thinking about transformers, right? So this is multimodal in the sense that you're able to take a picture and you're able to translate that into words in the picture using the exact same architecture as the words to words transformers. So this is, I think, a very exciting thing. On the right here is something called DALI, which was released by OpenAI also earlier this year. And this is even more interesting because just like the first example that I had given for GPT-3, where the network using a language model started with on social distancing and then started building up a lot of different words after it as a essay. In this case, what was given to the network was, can you create a chair that looks like an avocado? And none of these pictures are real pictures. These pictures were actually generated by this network called DALI. So in this case, you're going from a picture to a word. And in this case, you gave a sentence and said, I need a picture of a chair that looks like avocado. And this is what the network came up with. So this is, I think, the next forefront for transformers. That's one of the main reasons we said NLP transformers. We are working with language and language only. But I think in the next few years, you will see people starting to mix, pictures with words and words with pictures, and transformers being able to generate interesting things that come out of that architecture. So that's, I think, the more exciting piece. If you're not familiar with DALI, you should Google it. It's a really nice architecture. It is also based on transformers, and it's really amazing the kind of examples that they show on the DALI website. So I'll stop here and answer any questions. I may have gone over quite a bit, but I hope that's okay with me.
No, this is great. This is great, Sumitri. I got a quick question real quick, just on that last slide. I thought it was cool. You're talking about words to images and images to words. I started thinking about sound, audio. Not sure if you've done any audio analysis, but audio to pictures, you can start picking out the waveforms, right?
Yeah, yeah. So there is a transformer architecture called wave to back, and it uses exactly that same architecture where you take pictures, smaller pictures, or not pictures, but spectrograms
Mm-hmm.
of your audio, and basically starts translating the spectrograms of your audio to words that
Yeah.
already exists.
Yeah, it's fascinating just how it's all about data and then being able to transform them back and forth.
Yeah.
Yeah, if anybody wants to unmute, I guess, ask any questions right now, please go ahead.
Okay, I'll ask a question, Sumitri.
Yeah, yeah.
Can you go to slide 51? I have a question about that. Like 51, the third last or whatever. Yep. Okay. So I can think of two ways to do this. I'm just wondering how you guys did it. So one way is just use a transformer. It seems like you guys used a BERT transformer, then fine-tuned it, then fed it a bunch of data where, oh, if this is the document, then this is the origination date, this is the borrower name, da. Okay, and then, that's it. Like gave it your test data, validated your model, then gave it and called predict, and it figured this out based on the accuracy you gave, right? That's one way, right? Did you guys do that? I'll suggest another way, and you might not have done it at all, right? So the other way I was thinking is you can use third-party libraries like Spacey and other things. Spacey is also transformer based now, but you could use n number of libraries, right? Given a document, to convert it into name entity recognizer. So it just blindly says, when it sees a name, it says it's a name. It sees a, I don't know, a date, it says it's a date. It sees money, it says it's currency, whatever, right? And then create a RNN on top of it. And that kind of figures out, oh, this date is origination date. This name is borrower name, right? That would be two-step approach, right? And that when you're finally trying to predict, you would do the same. You'd first convert it to any or the entire document and then feed it into another RNN. Just curious what you guys did.
Yeah. So first of all, thanks for asking the question. So we did 2 or 3 things. So each one of these here is a different RNN model.
Okay.
So we use an ensemble of all of these things as the first thing to do. And I didn't go into too much detail about what we used, what each of these is. So if I can go back to this picture here. So we have this model here, which is basically what you described as the first way, right? Use BERT to fine tune BERT. We didn't stop at BERT. We also used other transformers, XLNet and RoBERTa and other things. And so some of them are in that, not all of them. And then this is to take the embeddings from BERT, but at the same time, we also take embeddings from the character RNN and the Elmo RNN, and we stack them together to create this LSTM on top. So this LSTM is trained, just like you mentioned, right? You take Spacey and then train an LSTM on top. Yes, that's exactly what we did. So we trained this LSTM here. The advantage of doing it this way compared to this way is that we not only just pick up the embeddings that are coming out of this, we actually can do these kinds of things, right? Let's just go to the second last layer and pick out that one. Or take the weighted sum of all the 12 layers. And the whole point of going through these these probes and trying to basically give a meaning to each of these layers is that they hold something valuable that you could use in your named entity recognition. So that's one thing. If that didn't come out too clearly, thank you for asking the question. I just want to bring that out. The other thing I wanted to say is it's normally people use named entity recognition for 4 classes, which is the name of a person, a name of an organization, and then a date. Date is actually not part of the top 4, but and those. So those are pre-trained models, and if you get Spacey or even for BERT, you get a model that is pre-trained for these 4 things. And it so turns out that, for many reasons, I could not bring out everything that we do here, but only a few of these meet the date and the name kind of things. So if you take the governing state law, or the alternate base rate, and then, or the rate reset frequency or payment frequency, for example, it could be something like the first day of every September, or something like that. And that's your class. So that's what you need to, your class is not one of those 4 standard classes, which is part of the Cornell NER set.
So you have to fine tune.
Yeah, you have to fine tune on your class set.
Yep. Okay, thank you.
Hi, Sumitri. I've got a question for you.
Yeah.
So do you see NLP applications in compliance? And to share context, I used to work for MoneyGram in their compliance department. And when I was there, I started to explore using NLP to analyze our consumer complaints data to look for any trends or patterns there, especially around Dodd-Frank. So as you think about other applications where you can use NLP and US Bank, and for compliance in particular, do you see any value there?
Yeah, definitely. So I don't know how much I can talk about compliance applications that we are currently working on, but we are actually using NLP models and transformer models for compliance. Tina, do you want to venture in and talk a little bit about?
Yeah, so great question, Danica. I think, in the financial industry is highly regulated, and there's a lot of compliance as well as customer privacies and fraud detections, and you think about AML too, right? And all that kind of things. One of the biggest thing in the industry, the financial industry right now, is not just compliance, but also automations. So most of the time, what we use right now, using all of these NLP and deep learning techniques, are to, number one, just automate the current compliance audits and all that kind of process that currently are pretty manual, right? And then from there, we would try to apply into compliances, but obviously we always have to consider the AI ethics, AI bias, and all that stuff too. So in terms of productionalizing this and using this, there's a lot of processes and rules and regulations that we have to go through to make sure that everything is done correctly. But I think to answer this questions a little bit on the other side, is we use this a lot for automation purposes right now.
That's fantastic. Thank you both.
Yep. Yeah, and I also brought up this interesting article on molecular transformers. So if you think about transformers and how we are putting sequences, you can also put large molecules like lipids and carbohydrates and things like that as input to a transformer and try to predict all the equations or all the reactions that it could be a part of. And this very recently came out in Nature, which is called a molecular transformer. My background is chemical engineering, as I said in the beginning. So you can actually do some interesting stuff with molecular transformers. And here are a set of reactions that a transformer is able to predict. And they actually go into details about, is this actually patented by the USPTO or not, and things like that. But if you are interested in this kind of stuff, you can look at this paper. It is, I mean, the Google term for this is molecular transformers. And there are a bunch of new reactions that the transformer is able to predict, although there are also certain transactions or that certain reactions that it is not able to predict correctly. But if you are somebody who's looking for a new drug or a new molecule, you, instead of trying out the different combinations and permutations, you could use the transformer to narrow down that list and maybe try those first. And this is in pharmacy and in other areas. This is one of the hot topics right now. Is going after using AI to predict new molecules.
Excellent, thank you.
Yeah, I've actually gone ahead. Tina had shared actually a link to the NIPS, I guess it was conference, Tina, that happened back in 2020. And so I just posted that in the chat here, and lots of videos and other papers, I think, associated with this conference that went on, and machine learning for health. So how do you put that out?
Quick question. It seems like that would be a very good way to identify things like generic drugs, or how to build up generic drugs and say, all right, this is the formula for whatever. Here are some reasonable variations of it. Would you see that as a use of this?
Yeah, that's the hope, that a lot of the pharmaceutical companies are going after this type of technology now.
I'm having flashbacks to organic chemistry, because that was the thing that killed me.
I'm trying to understand that the sequence or cascade of chemical reactions from the gene down to where there's a problem caused in the body that results in the disease. And they can be quite long, quite large, and they can be the next cell over, or they can be in the other side of the body. So there are a lot of paths that I have to think about. And then of course the reactions themselves.
Yeah. I mean, it's not a problem that is solved by the transformer end to end, I don't think. What people are looking at this type of technology is to say, okay, now I know that the reactions that this molecule has to do to cull the disease or basically break the disease pathway. What molecule does this? And then you basically ask the transformer to come up with candidate molecules that will do that for you based on training of different other molecules.
So just also a shameless plug here. The Neuro IPS conference, like Sumitri and I mentioned, as well as the link that I just sent to Justin's, it's going to be virtual this year. It's pretty affordable. And usually it's very, very, closed to, you have to be admitted with papers to even get to go to the conference. But the last couple of years being virtual, you can actually just apply and go on to these events and all of this knowledge transfer base here. So the entire data science team will be on virtual at NIPS this year from US Bank. So if you want to kind of get to know our teams, talk to our leaders there too, I would highly recommend this is the place where you get to meet all of those top researchers in the world, as well as meeting our team members there.
Yeah, I mean, also a shameless plug-in to if there are anybody in the audience who are students, or if you know of students who want to be part of our team for an internship next year, in next summer, we are just opening up those positions, and specifically in the AI team, I'm looking for graduate level students who want to intern with us. And if you know of anyone, please encourage them to apply at US Bank.
Excellent. Well, great. Boy, I appreciate all the information you shared tonight, Sumitri and Tina, with the group here. I think we've been getting lots of comments and stuff like that, saying thank you to everyone, and just a very, very good session. So appreciate everyone for showing up tonight. Sumitri and Tina, thanks again. I think I'll post, we'll get your contact information. It's out on the Meetup site as well, so people can contact you through our Applied AIMN Meetup group. And I think if there's anything else you guys want to say before the end of the night, I think we'll call it an evening. It was a great evening.
Yeah, thank you very much for this opportunity, and hopefully, you have a new appreciation for transformer-based models. And if it was repetitive for people who are experts in this area, I apologize, but I had a lot of fun presenting this stuff.
Excellent.
Yeah, thank you so much for having us.